Every fall, a combine harvester rolls through a cornfield at 5 miles per hour. A 40-foot header, 200 bushels per acre. Inside, hundreds of sensors, measuring grain flow, moisture, protein content, separator loss, ground speed, header height, and GPS position, all simultaneously. A single pass generates a yield map accurate to within a few % of scale weight. That map decides next year's seed rates, fertilizer zones, and irrigation schedules. Get it wrong by 10%. That's $90,000 in bad decisions on a 1,000-acre farm. The math holding it all together. The same Kalman filter algorithm that guided Apollo spacecraft to the moon. This is sensor fusion. 5 layers of it. From raw voltage to the cloud. Let's go. At the top of every combine's clean grain elevator sits an impact plate. Grain hits it. A load cell measures the force. Simple physics, mass times velocity equals momentum change. Except it's not simple at all. At high flow rates, above 3 kilograms per second, accuracy is plus or minus 15%. At low flow, field edges, headland turns, error explodes to 60%. These numbers come from peer-reviewed field studies, not marketing brochures. Why? Material buildup dampens the plate. Combined vibration creates phantom signal. Slope throws off the force vector. A machine pitched forward reads high, pitched back reads low. One sensor, 4 sources of error. And this is supposed to tell you how much food you grew. The aftermarket solved it first. Precision Plantings Yield Sense redesigned the sensor from scratch. A new flow sensor at the elevator top with a shaped paddle for consistent grain release. The company claims 1 to 2% of scale weight accuracy. 1 calibration per crop per season. But most farmers still run the OEM impact plate, and most yield maps are noisier than they look. Knowing how much grain flows through the elevator is half the story. The other half is what's in it. Meet the Harvest Lab 3000, a near-infrared spectrometer, the same technology trusted in pharmaceutical labs, bolted to the discharge spout of a combine. It fires infrared light through a glass window onto the grain stream. Different molecules absorb different wavelengths. Moisture absorbs one band. Protein absorbs another. Starch, fiber, sugar, each has a spectral fingerprint. According to John Deere's specs and independent DLG testing, 4,000 readings per second. This sensor analyzes grain composition over 100 times faster than your phone screen refreshes. But NIR has a dirty secret. Accuracy depends entirely on calibration models, mathematical curves trained on lab-verified samples. Wrong model. Every reading drifts, and those models are proprietary. Claas runs its own. AGCO runs its own. John Deere runs its own. None are interchangeable. Your $15,000 sensor is only as good as the calibration curve the manufacturer gives you. And you can't retrain it yourself. Behind the combine's threshing drum and cleaning shoe, grain that didn't make it into the tank hits a thin film of PVDF, polyvinylidene fluoride, a piezoelectric polymer. When a kernel strikes the film, it generates a tiny electrical charge. Straw and chaff hit differently, lighter, softer. The sensor discriminates grain from trash by charge amplitude and frequency. This is how a combine hears what it's losing. Fendt took this further than anyone. The ideal combine carries 52 acoustic sensors distributed across the entire threshing, separation, and cleaning system. Not just behind the shoe, everywhere. Like a doctor pressing a stethoscope to 52 points on your chest. Except the patient is 30 tons of steel moving through a wheat field. These loss sensors feed directly into Idea Larvest, Fendt's auto-adjustment system. Operator sets a target, minimize loss, minimize grain damage, or minimize trash in the tank. The system continuously adjusts rotor speed, fan speed, and sieve position. No human intervention. According to university extension studies, a poorly adjusted combine can lose over 10% of the crop. On a 1,000-acre corn farm at 200 bushels and $4.50 a bushel, that's up to $90,000 on the ground. Sensor Fusion's job, Bring that under 3%. So we have mass flow from the impact plate, moisture and protein from NIR, loss rates from piezoelectric film, ground speed from radar, header position from hydraulic sensors, and centimeter GPS from RTK. 6 data streams, all noisy, all biased, all at different sample rates. How do you turn that into one number, bushels per acre, wet or dry, at this exact GPS coordinate? Kalman filtering, the same class of algorithm Rudolf Kalman published in 1960, the same math that guided Apollo spacecraft to the moon and still guides every GPS receiver on Earth. Research papers confirm Kalman filters are used to process combined sensor data, smoothing noisy signals from impact plates and loss sensors. It works in 2 steps. Predict, use a physical model of grain flow to estimate what the next reading should be. Update when the actual sensor reading arrives, blend it with the prediction, weighted by how much you trust each source. Noisy impact plate at a headland turn. Trust drops. High confidence NIR moisture reading. Weight goes up. The filter continuously rebalances. Claas calls their version CMOS automatic. A laser sensor plus feed height sensor in the feeder housing. The system auto-adjusts 5 settings: rotor speed, rotor covers, fan speed, upper sieve, lower sieve. 4 strategies: max throughput, grain cleanliness, fuel economy, or balanced. The result is a combine that optimizes itself faster than any human operator can. Even a first-day trainee gets expert-level harvest quality. Every few seconds, the combine stamps a data point: GPS coordinate, yield, moisture, protein, loss rate. Thousands of points per field, millions per farm. After harvest, these points become a yield map, and that map is worth more than the grain itself. Because next spring, that map feeds a variable rate prescription. Low-yield zones get less seed and more nitrogen. High-yield zones get denser planting. The prescription pushes down to the planter through the same CAN bus we covered last time. Field trials consistently show precision prescriptions improve corn yields. Even a modest 2 extra bushels per acre at $4.50 adds up. On a 1,000-acre farm, that's $9,000 per year from better data alone. Larger gains are documented, but vary by region and practice. But here's the problem. John Deere reports hundreds of thousands of connected machines monitoring hundreds of millions of acres. A massive share of U.S. cropland feeding data to one company. Ag data companies say you own your farm data, but read the fine print. Their licenses typically grant broad rights to access, use, reproduce, and modify that data. The combine that mapped your field, its calibration software, is locked behind a dealer login. The FTC filed a complaint against John Deere in early 2025 over exactly this. A federal judge denied Deere's motion to dismiss. Hundreds of sensors per machine, hundreds of millions of acres of data, and a legal fight over who gets to read the map. 5 layers: impact plate, NIR spectrometer, piezoelectric loss sensors, Kalman filter fusion, and a data map that might be worth more than the harvest. Next time, how robotic mowers navigate a yard with no boundary wire, using RTK GPS and computer vision. Hit subscribe before your combine's yield data gets more followers than you.